Are we there? All right, looks like we're live. Apologies about earlier today. We weren't able to have a live stream. We had some technical issues getting the broadcast technology hooked up to YouTube here, but looks like we're good to go right now. I'll have the stream going for as long as necessary right now. A couple things that I wanted to go over, or at least I was thinking about reviewing. Haven't heard anything from anyone yet about if there's anything in particular they want me to review, but what I was thinking about doing was a couple of the problems from yesterday, the solving quadratic equation section, and then probably going over a couple problems from tonight's homework. That was my thoughts. Let me know if you have anything else you'd like me to review. Starting off with section 6.7, I figured might as well go over the exit tickets from that section. So let me throw that up on the screen really quick. The exit tickets were the polynomial 6x squared plus 5x minus 21 equals 0. Now, when it came to solving quadratic equations, people needed to first understand what you're being asked. Because a lot of people, I guess I would say, solved part of the problems. But then when it came to finally solving the rest, they tended to back out. So we want to make sure that as we go through, we're able to not only solve these problems, but understand what we're looking for in these answers. So in the past, I would have given you the polynomial 6x squared plus 5x minus 21. And I would have said factor this. But now I'm asking you to actually go ahead and solve the equation. So when I say solve the equation, I want you to figure out what x is. So I'm going to write here, find x. Okay? Now, as we go and we find what the value of x is, we need to think about how we can go and do this. We learned yesterday that our traditional methods for solving for x or solving for variables algebraically aren't going to work. So what we need to do instead is the zero product property. The zero product property said factor down the polynomial and make sure the polynomial is set to 0. So if it's set to 0, factor it down, and then set each of its factors equal to 0. All right, we have the polynomial 6x squared plus 5x minus 21. I'm not seeing a GCF in there, and since it's a trinomial, I'm going to have to do the AC method. So 6 times negative 21. Let's see what we get here. That should be a negative 126. If we list the factors of that, we have negative 1 and 126. We have negative 2 and 63. We have negative 3. That's terrible, 3. Negative 3 and 42. Let's see. We have 6 and 21. You can probably hear my calculator going in the background. That's because I actually like to list all these factors out. I hope you have a system in place right now to actually go and list factors and making sure that they're listed in an organized way. Remember when we were going over factoring, we said that was pretty key, making sure your work stays as organized as possible. And I think that's pretty much it as far as the factors go. And of course, we can have the other numbers being negative, so I'll list those as well. If my stylus will work. Here we go. All in all, doesn't take me very long to list all of these factors now, does it? Once I have these listed, I need to go and identify which pair of factors adds to 5 and make sure it adds to positive 5. So let's see, it looks like, which one is there? Here we go. Negative 9 and 14 seems like it'll work. So I will rewrite the polynomial as 6x squared minus 9x plus 14x minus 21. I've just subbed it in. Now I can group group the pairs together and factor this by grouping because it's a 4-term polynomial. Let's find the GCF for the first group. It looks like it's just a 3x. So we're left with 2x minus 3. And then for the next group, 14x and negative 21, it looks like 7 is the GCF there. So I get 2x minus 3. Again, now that they have a common binomial, we can factor that binomial out. And what we're left with is 3x plus 7. These are the factors of the polynomial. So all that this work is doing is letting us rewrite the problem. Instead of having the 6x squared plus 5x minus 21 equals 0, we can say 2x minus 3 times 3x plus 7 equals 0. How does this help us solve the problem? Well, if you remember, the zero product property says that if you are multiplying two things together and they equal 0, that means one of those things that you multiply by has to be 0. So we can set 2x minus 3 to be 0, and we can set 3x plus 7 to equal 0. Now let's solve for x in each situation. 2x equals 3, x equals 3 halves. Over here, 3x equals negative 7, x equals negative 7 thirds. These are the two answers that we will get for the first problem in our exit ticket. We have 3 halves, and we will have negative 7 thirds. So in this situation, what we're saying here is these are the two possible solutions that could get us 0. Students had asked me before, isn't there only one answer for x? I guess you could say that. Like sometimes students say, well, if you were making up this problem, right, you wouldn't have two solutions. You would have just one solution. So how do we know? Well, I guess if I was saying what number satisfies this, really you would say either of these. So if I said, because I was going back and forth with the student, and essentially their question came down to, okay, what if Mr. Linford is playing a game and he says, okay, I'm thinking of one solution for this problem. What is it? Well, you wouldn't know exactly what solution it was. You would have a 50-50 guess. I'm either thinking of 3 halves or negative 7 thirds. But that's not really the case right here. We need to kind of get out of our head that there's only one answer for x. In fact, the degree of the polynomial tells us how many solutions there will be to this situation. Anytime you set a polynomial equal to 0, its degree will tell us how many solutions there are. Okay? The reason for that, it comes from the fundamental theorem of algebra, and it's a little bit more complicated, but I'm hoping that we still have time this semester to get into it a little more. If you go and take the Bridge to 176 class, I'm hoping in that class we'll definitely have time to kind of explore this topic a little bit more. Matthias, you were saying that you got those answers, but it marked it wrong. Yeah, that's the situation with Edulastic. So if you check back in my emails, I mentioned that there's the problem. Really, the situation is if you don't enter it in exactly as how I've typed the answer key, then it's going to mark it wrong. So some people had the negative on the 7 or the negative on the outside, and it would mark that wrong. If they put a space in between the two answers, then it would mark it wrong. All stuff like that. So again, don't worry. I go through all of the all of the problems on the exit tickets and everything through Edulastic, and I check over to see if the student entered it incorrectly and they just marked it wrong or not. Now, if there's no questions about that, let's move on to problem 2. And again, let me know if you have any questions or comments. Leave them in the live chat for me. And if there's anything in particular you'd like me to go over, let me know, okay? Right now, I think I'll probably cover the second exit ticket problem. Again, we have a quadratic here. And remember, a quadratic is a degree 2 polynomial. We want to factor this down. Now, in this situation, I do notice that there is a GCF here. Okay? So I'm looking at this and I'm saying, hey, 12, 2, and 4 all have something in common. And that's 2. So let's factor the 2 out, and we're left with 6x squared plus x minus 2 equals 0. Okay? Now, in this situation, I can forget about the 2. All I really need to do is work with 6x squared plus x minus 2 equaling 0. Sometimes students say, well, why can you forget about the 2? Well, think about it like this. If I have 2 times this, whatever this number is going to be, this one polynomial equaling 0, well, 2 isn't 0, so that means this would have to be the thing that's 0. Okay? So really, I don't care about the 2. It's never going to be 0. This is the thing that I need to break down. Another way that you could think about this is just divide the 2 over, and you get 6x squared plus x minus 2 equals 0. Okay? So really, we're just working with the factors. We don't need to work with the number. So let's see. We have, we're going to have to do AC method on this. That's okay. 6 times negative 2 is negative 12. The factors are negative 1 and 12, negative 2 and 6, negative 3 and 4. Then we also have 1 and negative 12, 2 and negative 6, 3 and negative 4. Which of these adds up to give us a 1 or a 1x? That is going to be negative 3 and positive 4. So we have 6x squared, and then we have a minus 3x, we have a plus 4x, and we have a minus 2. And we set both of those equal to 0, or the whole thing equal to 0. Since it's a 4-term polynomial, we need to go and factor it down by grouping. So the first group has a GCF of 3x. So if we factor that out, we're left with 2x minus 1. And then if we factor out the 2 from the second group, we're left with 2x minus 1 equals 0. Again, we see that there is a common group here, or a common binomial, that we can factor out. So when we pull out the 2x minus 1, we're left with 3x plus 2 equaling 0. So here are the two factors, the two things that when multiplied together get us 0. So let's take a look at the first factor, 2x minus 1. What could I plug in for x to make that 0? Well, if I solve for x, I get 1/2. X equals a half. So if we plugged a half in here, we would get 0. Then we might say to ourselves, okay, well, what about 3x plus 2? What number do we have to be aware of plugging in for x that would make this 0? Well, again, just solving it like normal, we would end up with x equals negative 2/3. So that's the other number that we would plug in to get 0. So these are the two situations that would give us solutions to this equation. These are the two solutions that would give us 0. Now, I want to point out why the equations are always set equal to 0. Sometimes you might see an equation, I think I did this on the homework a couple times, you might have seen something like 12x squared plus 2x equals 4. And students say, well, can't I just factor this? We would end up with, pull out a 2x, you're left with 6x plus 1 equals 4. And they would say, well, what's the issue with that? Well, the problem is I can't use the zero product property now, can I? I'm saying that these two things are multiplying together to give us 4. Well, then they could be all kinds of numbers, all kinds of fractions. There might even be infinitely many solutions that we could have. It's when we have it set equal to 0 that we can use the zero product property. It's when the multiplication problem, the two things multiplied together equals 0, that I know for a fact one of them has to be 0. So that was my review of the exit ticket problems from yesterday. Hope that made sense to people. If not, let me know in the live chat. Ask me some questions. Let me know if I need to go over anything more. One of the areas that people seem to mess up on was their work often stopped right here. They factored everything down and then they left it. Remember, we're trying to figure out what x is. We're actually solving equations now. Pretty much all the work that we've been doing this semester with factoring, with working with rational expressions, working with radical expressions, has built us up to this moment, solving all these nonlinear equations. We've gone through and we've practiced how to simplify everything. Now we're putting it together to actually go and solve an equation. So this was the one of solving quadratics, one of the main types of polynomials we studied. And then today, you're going to be studying how to solve rational equations. What happens when I put polynomial rational expressions, fractions, things with a numerator and denominator that are polynomials. What happens when I put those into equations? And how do you go about solving those? And then tomorrow, we're going to go about working with how to solve square root or radical equations, things that have roots within them. So hopefully you're remembering all these different techniques for simplifying and combining things down. I'd like to take a couple minutes to go over, I'm not going to go over the exit ticket problems yet. I can do those on Monday during our live stream, but I'd like to take a minute to go over a couple of the homework problems from tonight's independent and advanced practice, in particular the word problems that we are going to be exploring. There are application problems in this section. I like giving these application problems because, one, it's nice to see how these nonlinear things are working, but additionally, the application problems that you're going to see for rational expressions, the work problems that we're going to get to, are common problems that you see on SAT, PSAT, and all the formats for standardized testing. The first thing that we should probably do is, I'm looking at 7.6, section 7.6, and I'm looking at problem number 1 from the independent practice. This problem is 1 over x equals 1 over 4 minus x. Now, in this problem, we have a fraction set equal to a fraction. That's kind of how we start in our solving of these radical equations. What can we do to solve this for x? Well, really, before we begin trying to attempt to solve for x, we need to get rid of the fractions, okay? Because x here is trapped in the denominators. So our goal is to bring it up to the numerator, get rid of all of the fractions. So what technique do we have for getting rid of fractions? Well, clearing the fractions, right? And we would clear the fractions by finding a common denominator. What's a common denominator between x and 4 minus x? Well, hopefully you remember that really our trick was to just link them together. So the common denominator would be x times 4 minus x. That's going to be our common denominator. So I can multiply that to both sides, x times 4 minus x over 1 times 1 over x, and 1 over 4 minus x times 4 minus x. So we have the original equation here, and I've just multiplied both sides by the common denominator. I won't simplify anything yet or cancel anything out. I'm just going to actually multiply. So we multiply across for fractions, and then we'll see what cancels out. All right, we've multiplied across, and since we found a common denominator, we should be able to cancel the denominators out. So the x's are going to cancel out here, and the 4 minus x is going to cancel out with the 4 minus x here. And what we're left with is 4 minus x equals x. There's an alternative way to getting this. Students were asking me, Linford, can we finally cross multiply? The answer is yes. You can cross multiply here. That's something that people have been wanting to do all semester long. When you cross multiply, you would get a 4 minus x equaling x. Cross multiplying is shortcut clearing fractions. That's where it comes from. That's the basic idea behind it. It's a shortcut to clearing fractions. So if you have a fraction equaling a fraction, you can do cross multiplying. But keep that in mind. A fraction equaling a fraction. or a rational expression equaling a rational expression. That's the only time you can go and do this method for clearing or for cross multiplying. Now let's go ahead and solve this. I can add x to both sides, and when I add an x to both sides, we get 2x equals 4. Divide both sides by 2, and you get 2 equals x. There is our final answer. X is equal to 2. Now, one of the things I really stressed in the video, and of course I stressed it so much that I forgot to do it in the last problem, is you got to check your work. All right? You have to make sure, you got to go back and make sure that your answer that you found is in fact a solution. So let's start by plugging it back in for x into the original problem. The original, not any simplified version or anything, just the original problem is the one we want to plug it back into. So we have 1 over 2 is equal to 1 over 4 minus 2. So a half is equal to a half. It works, okay? So I went through and checked the problem, and I can verify to you that it works. This is, in fact, a solution. You'll see on the homework tonight, all of the problems that I do, I've checked. And some of them, I will find, I solve for x and get a solution, but when I check it, I find that they aren't solutions, in fact. They're what are called extraneous solutions. It's a possibility that you can do all this work, solve something for x, and then what you end up with is, in fact, not a solution. When you check it, it actually doesn't work. The reason for that, it gets kind of complicated, but basically, when we're solving things that have fractions to them, when we're solving these rational equations, remember, rationals don't have infinite domain. They have domains that are limited and restricted. Remember, they have asymptotes. So when we go to solve these, you'll notice that we immediately turn them into linear equations to solve. Linear equations have infinitely many, or have a domain of infinitely many values. So that's partially why this is kind of an issue. We're taking something that has a restricted domain and converting it to something that has an infinite domain and then trying to find a solution. That's basically why we sometimes have the situation of extraneous solutions. So that situation where we have a fraction equal to a fraction is similar in problem 3 from the independent practice, where we have 8 over 9x minus 1 equaling 5 over 3x plus 2. I'm just going to cross multiply. So we have 8 times 3x plus 2 equaling 5 times 9x minus 1. We end up with a 24x plus 16 equaling 45x minus 5. I can subtract 24x from both sides. We have 16 is equal to 45 minus 24 is 21x minus 5. I'll add 5 to both sides, and I'll end up with a 21 equaling 21x. So that means x should equal 1. And that would be our solution for this. X equals 1. Again, let's go back in and check it to make sure that this works. 8 over 9 times 1 minus 1 should be the same as 5 over 3 times 1 plus 2. Well, that becomes an 8 over 9 times 1 is 9, minus 1 is 8. And then we have 5 over, 3 times 1 is 3, plus 2 is 5. Oh, so this is just 1 equals 1. Yep, it works. Let's take a little bit harder of a problem. Let's try to get a little more of a challenge going, this time where I have multiple fractions to work with. So as I'm looking at the independent practice right now, I'm looking at a problem like problem number 7. So let's take 7 from the independent practice, and that one is x over x plus 6 equals 72 over x squared minus 36 plus 4. In this problem, we are going to solve for x, but here's the trouble. We can't cross multiply now. What we need to do is actually go through and clear the fractions like we used to do when they were just when the fractions just had numbers on the top and bottom. Now they have polynomials, but that's okay. Let's go ahead and clear them. We need to figure out what is the common denominator here, or some people might say the GCF, but let's just say what's the common factor that we have with x plus 6 and x squared minus 36. And I guess we could say that's over 1. Well, the first thing I would say to do before we find the common denominator is let's try to factor everything down. That way it's easier to see what's going on. And as I factor x squared minus 36, we get it to be x plus 6 and x minus 6. Okay, now I can easily see what a common factor is. A common factor has to include the x plus 6 and the x minus 6. So let me write that in red here. The common factor would be x plus 6, x minus 6, or the common denominator, I should say. So that's the thing that I'm going to have to multiply to all of the fractions to clear the denominators. So let me try to fit all of that work here. X plus 6 times x minus 6 over 1. This is something I tried to do on the answer key, just so you can see all of the work that I'm doing to simplify everything. Again, you don't have to show all of that work, but it's probably helpful when you're going through, and especially if you need to check your work or anything. All right, I'm going to multiply the x plus 6 and the x minus 6 now to the expression with the 72. And I hope I have enough room here. And then plus, well, that's just 4 times all of this. X plus 6. And actually multiply these across if you want. I'm just going to go and start canceling things out. Okay? If there's a factor on the top and the bottom that are in common, I can just cancel them out. So x plus 6 and x plus 6 are going to cancel. On the top here, I have x plus 6 and x minus 6. That cancels out with both of those on the bottom. And then nothing cancels out here because it's all on the top. So what are we left with? We are left with an x. Let me rewrite that. We're left with an x times x minus 6. Oh my gosh, of course the stylus suddenly wants to not work. X minus 6 equaling 72, and then plus 4 times x plus 6, x minus 6. Okay, all that we did for this problem was we cleared the fractions. We said before we can even attempt to solve for what x is, we have to get it out of the denominator. So we did. We cleared the fractions. Now everything's essentially just a number. It's no longer in a denominator. So how do we solve it from here? Well, you're going to have to simplify, multiply all these things through, and turn it into a quadratic, okay? So let's distribute the x. We got x squared minus 6x. Oh, this stupid stylus, I swear. Equaling 72 plus 4 times x plus 6 times x minus 6 is x squared minus 36. We have an x squared minus 6x equaling 72. Let's distribute the 4. We have a 4x squared minus, oh boy, what is that? 36 times 4. Let's see, 30 times 4 is 120. And 6 and 4 is 24. So 24 and 120 should be 144. And now we can go ahead and keep simplifying to get x squared minus 6x equaling 72 minus 144. Let me see. 72 minus 144 is, a negative 72. I probably could have figured that. And let's go ahead and You know, I could blame the stylus for the handwriting, but let's be honest, it's just my bad handwriting. Let's move the x squared over, and then we'll add the 6x over. So we end up with 0 equals 3x squared plus 6x minus 72. Okay. We've gone through, and we got rid of all the fractions. Now, it's a standard equation to solve. So I go and I distribute things. I get all the x's to one side. I'm noticing sometimes students say, well, how do you know that this is going to turn out to be a quadratic equation? I just noticed that there's x squareds in the problem. So I know it's going to be quadratic. So with that, I'm going to say, well, I'm going to solve it with the zero product property. So might as well get all of the terms to one side and 0 on the other side. And now I can go ahead and solve this like a standard quadratic. I'm going to need some room, so let me jump over a page. 0 equaling 3x squared plus 6x minus 72. I think that's what it was. All right. Now I need to factor this down. I'm looking here and I'm saying, there's probably a GCF. It looks like 3 is a GCF. So I can factor a 3 out to get x squared plus 2x minus 24. So really, all that I need to keep breaking down is the x squared plus the 2x minus 24. Well, this is very easy to factor. Let's see. It's going to be two binomials. The leading terms are both going to be x's. Then I need to think what multiplies to give me negative 24, but adds to give me 2. I'm thinking 6, positive 6, and negative 4. That would give me negative 24, but add to give me positive 2. And here are my two factors. They're both set equal to 0, so let's solve each one. X plus 6 could be 0, so I need to be careful with negative 6, because if I plug in negative 6, I'm going to get the whole thing to be 0. And then x minus 4 could be 0, so x could be 4 as well. So if I plug in either negative 6 or 4, I will get this to be 0, okay? So we're going to say, here are our two solutions. But wait a minute. These solutions solve the quadratic. Do they actually go and solve the original problem? So that's the thing we have to check. So let me swap colors here, and let's check each one of these. We're going to start with negative 6. I'm going to plug in, so it's negative 6 over negative 6 plus 6 equaling 72 over negative 6 squared minus 36 plus 4. All right. Obviously, take a look here. Negative 6 over 0 equals 72 over, well, 6 squared. Negative 6 squared is 36. 36 minus 36. 0 again. I have 0 in the denominator here. This is a big error. That's not going to work. So it turns out this is what's called an extraneous solution. It solves the quadratic, but it doesn't solve the original problem, the radical. The rational. So that's the thing. This is where we run into some trouble when we convert something that has a restricted domain to something that has an infinite domain. So 6 is not going to work here. Let's try 4. We have 4 over 4 plus 6 equaling 72 over 4 squared minus 36 plus 4. So that's 4 over 10 equaling 72 over 16 minus 36 is negative 20 plus 4. And, okay, let's simplify 4 over 10. That is 2 over 5. And I'm going to use my calculator to do negative 72 over 10. I'm sorry, over 20. And I'm going to add 4 to that. And as a fraction, that number is 2/5. So it works. 4 actually goes and solves the original problem, but negative 6 doesn't. So we are going to write our answers like this. Let me try to clear some space here. Well, I could probably just fit it down here. X equals 4. And then you can say x equaling -6 is extraneous. And here is how I want you to write your answers. Okay, you'll see that on the answer key where I write, here's both solutions, but one of them is extraneous, or maybe both of them work. Okay, things to keep a lookout for. Gene, you're saying that you were wondering where the 6.1 exit ticket came from. Oh, Gene, that is, check back in my email, that is for the factoring unit. Remember, for the factoring makeup test for Unit 3 that we talked about doing before we went to fully online, I said I was going to put all of that stuff on under Unit 3. So if students wanted to do the Unit 3 makeup, just reread that email I sent the other day explaining about how Unit 3 is posted and available. People can go through and work on the sections through there. And then when they're done with all the sections in the exit ticket, I'm going to have the makeup test posted for people to work through. So you don't have to do section 6.1. That's totally up to you if you wanted to. Okay? Really, I'm not even putting those grades in PowerSchool. I'm just looking to see, before people go in, just jump into doing the makeup test, I want to make sure people are set with all the topics before they jump into it. So, good question on there. Let me know if there's anything in particular, by the way, you want me to go over. People seem to be fairly quiet today. Not too many people emailing me. Probably I'm wondering if people are still working on this section, but that's okay. What I'd like to do right now, why don't we try one from the advanced practice, and then I'd like to get into, well, you know what? Before we do too much of the same thing, why don't we try doing a couple application problems. I'm going to do an application problem from the first practice, for the independent practice, and then let's do some more problems maybe if people want from the advanced practice. So just in case people got to get running, I'd like to do a couple application problems, and then we'll go back to doing some more problems from the advanced. So let's get into section 7.7. By the way, 7.6 and 7.7, I group those together, right? 7.7 is really just, hey, application stuff. Well, I figured we can do all of that at once. So for this one, I'm looking at, I'm going to look at problem 2 first, 2 from the independent practice. And this is saying that you have a sink, basically, okay? You have a sink, and there are 2 faucets to it. So, all right, here's your sink. Terrible drawing, I know, but whatever. And you have 2 faucets. There is a cold water faucet, and there is a warm water faucet. So one of them provides cold water, one of them provides hot water. So the cold water faucet is left on. And if it's left on, like if you just flip the faucet open and let it run, it will fill up the entire sink in about 10 minutes. Okay? Now, if you left the warm water on, it wouldn't fill up in about 10 minutes, because we're going to say that the warm water takes a little bit longer because the water is going to flow a little bit slower. The water itself actually needs to heat up first. So we're going to say that it takes, if you just left the warm water faucet on, it would take about 21 minutes to fill the entire sink with hot water. Now the question is if you put both of them on, both the hot and both of the cold water, how long would it take for you to fill up the sink with cold and with hot water? So that's the question of work, And that's what these work problems are really getting you to think about. It's when you're trying to complete a task or to complete a job. One thing can complete that task in a certain amount of time. Another thing can complete that task in a certain amount of time. What about the both of them together? What if you work together? How can we do this? Well, in the video, I talk about the idea of the rate at which the job is completed. So I would say, that the rate of the cold water faucet is performing the job in 10 minutes. So that would be a 1/10 job completion. So it can complete one job in 10 minutes. Now, the warm water, or the rate of the warm water, I should say, the rate at which it completes the job, or the task of filling the sink, it gets that single job done in 21 minutes. So that's its rate for completing the job. The cold water is a 1/10 rate, and then the warm water is a 1/21 rate. Now, if I were to combine the rates, that means adding them together, what would I get? That's the idea of them working together. You're combining or you're adding them. So let me clear some space here. What we're doing is we're adding the 1/10 rate here and the 1/21 rate here. And we will end up with, let me grab my calculator, 1/10 plus 1/21. And I'm going to get that into a fraction, is 31/210. Okay, how does this help me? Well, take a minute and let's rethink about what this fraction setup is. Remember, the numerator represented the jobs completed, and the denominator represented the time. So, minutes. So we could say that before, the cold water would fill one sink in 10 minutes. The warm water would fill one sink in 21 minutes. What this is saying is together they could fill 31 sinks in 10 minutes. Okay, I guess that gives me a rate of time, but I don't want to know how long it takes them to fill 31 sinks. I want to know how long does it take them to fill just one sink. How much time is that? So again, if this fraction is jobs over minutes, so basically how long does it take them to fill one sink over how many minutes? Well, I can simplify this fraction so that it now has a 1 in the numerator. Well, how do I do that? Well, pretty simple. You can say, all right, the numerator's going to be a 1, but what's the denominator going to be? Well, leave it as x, and then just cross multiply. 31x equals 210. And if I solve for x, I get 6.77 minutes, roughly that. What this is saying is to fill one sink, it would take 6.77 minutes, roughly about that. Okay? The idea here is when you combine the rates, you get the new total rate. How long does it take to complete one job? So this is going to be the general idea that we use to solve these problems. There is a formula that we are going to stick with, and I think I talked about that formula in the video, and I definitely show it on the answer key. The formula says that you take how long it takes to complete the job, one job and how long it takes to complete the job for the first faucet, the one job and how long it takes to complete that for the second faucet, and that's equal to the one job and x. X being how long it takes them to complete together. So x equals how long it takes both to complete one job. You'll notice I'm saying phrases like a job, a task, things like that, because that's really what we're representing here. How long does it take to complete this one objective that we have? Now let's go ahead and, let me try the problem from number 1 on the independent practice from 7.7. That one talks about, that's actually a funny one. I don't know if any of you watch the show Parks and Recreation. It's a hilarious show. If you haven't seen it. During episode, I think it's episode 18 of season 4, this is when Leslie Knope is running for city council. And in this episode, we have, as a small subplot, the characters Jerry and Donna are filling envelopes to mail out to people for Leslie's campaign. And I estimated they're probably sending out 10,000 envelopes. So they have to stuff these envelopes. Well, Jerry, who's usually messes everything up, is working at an incredible speed, and he loves filling out these envelopes. It's no big deal for him. He's organized and working well, and Donna's kind of amazed, like, wow, this is interesting. Jerry's actually doing well at something. So it starts off where Donna and Jerry are working together, and then sooner or later, Jerry takes over. So I kind of estimated based on when they started and looking at some of the footage and how much Donna got done and then how much Jerry got done, I kind of put this problem together saying, okay, they need to stuff about 10,000 envelopes. So Jerry, I'll say rate of Jerry, he can fill all 10,000 envelopes in about 18 hours. So he can do the one task in 18 hours. The rate of Donna, however, is a bit slower. Donna only worked for a little bit, and then she was going to call it quits because, time ran out. So she was going to pick up the next day. So she could get the one job done in about 144 hours. So it might take her a couple work days to get all 10,000 envelopes stuffed if she's just working by herself. Now, if they worked together at these rates, how long would it take them to complete the one task? Again, X here is the time it would take to complete this task if they work together. And again, we're assuming that they work at their consistent rates, like they don't take a break or anything. So all we have to do here is solve this equation. 1 over 18 plus 1 over 144 equals 1 over x. Well, I could clear this, or I can just add 1 over 18 and 1 over 144. I end up with 1 over 16 equals 1 over x. I could cross multiply and get x equals 16. So if they worked together, they could get the job done in 16 straight hours, which is roughly what they did. If you remember in the show, I think they stop at 4 in the morning. Gene, you're asking, is this what you think about when you watch TV? Yep, pretty much. How can you use this situation for a math problem? Yeah, that's pretty much what I do when I watch TV. It's really annoying to my friends sometimes. But I thought this was an interesting problem because, yeah, they're sort of working together, but it's one of those problems where you work together with someone and only one person is really doing all the work and one person kind of is slacking off. So you can kind of see how when they work together, how that affects the total rate. Actually, now that I'm remembering this problem, how long would it take them to do it? Well, 16 hours. But the problem was from the show, Jerry forgot to put something in the envelopes. So he actually had to do it all over again. So I guess technically he'd have to double the time for this one. Oh, Jerry. Well, whatever. Let's go ahead and I'm going to take a little bit more time, unless people have anything in particular they'd like me to go over. I was thinking about probably going over a couple from the advanced practice now, just to review a few of those problems, and then maybe go over a few of the advanced problems from the word problems as well. So let me know if there's anything in particular you'd like me to review or go over. But right now, I'd like to take a look at some of the problems from the advanced section. If I can find that. My papers are all over the place here. Advanced section. I'm going to say, let's go over problems. I want to go over a little bit more difficult ones. So I'm looking at problems. Let's take a look at something like, let's start with something like number 7. That looks like a good problem to begin with. Number 7 here. Sorry, I'm sure you can hear all my papers moving in the background. I started off all organized, and then that just stopped. So, all right, let's just get to this problem. Problem 7 says, from the advanced practice, come on, stylus, work. There we go. 7 from the advanced says -3 over x squared minus 7x plus 12 minus x squared plus x minus 12 over 2 equaling 10 all over x squared minus 16. Okay, again, before we can even attempt to solve this problem, what we're going to need to do is get the x's out of the denominator. Well, to do that, we're going to have to probably clear the fractions. You could make all of the fractions common denominators and add them together, but I don't know, I like to clear the fractions. It's actually less work that I have to show and a bit quicker. Well, before I can even attempt to try to find what a common denominator is, I better try to factor these polynomials down because I really don't want to have to multiply all of these together. So let's see. X squared minus 7x plus 12. That would be x plus 4. No, I'm sorry. X minus 4 times x minus 3. Because -4 and -3 give me positive 12, but they add to -7. Let's see, we have 2 over, what multiplies to give me -12, but adds to give me 1. That would be a positive 4 and a -3. And then x squared minus 16 is x plus 4, x minus 4. And let's take a look. What are all of the denominators grouped together? Let me write that at the top in red. I need an x to the 4th. I'm sorry, an x plus 4, an x minus 4, and an x minus 3. That looks like all of them. X minus 4, x plus 4, x minus 3. Cool. So that's what I'm going to multiply to all of these fractions. All right, I am totally going to run out of space here. So I'm going to have to do this on a couple lines, but I'm going to try to keep it color-coded. So x plus 4, x minus 4, x minus 3. Do you have to show all of this work? No, but it's sometimes nice to see all of the steps that are going on. And I just try to do this for you so you can have it on the answer key in case you ever have questions and want to see what I did. There's the first fraction that we're multiplying the common denominator by. Minus, all right, let's go with x plus 4, x minus 4, x minus 3. I'm saying to myself right now, why didn't I pick a smaller common denominator? And let's see, this is times, let me see if I have enough room. X plus 4, x minus 3, yeah, just enough, times 2. And then that's going to be equal to, I'll write it down here, x plus 4, x minus 4, what was that, x minus 4, are all underneath 10, and I'm going to multiply that by the x, the x plus 4 times x minus 4 times x minus 3. So we can go ahead and see now what would cancel out with what. Some of you are pretty good at doing this in your head, and that's fine. No big deal. Just try to make sure that you're being careful with what cancels out and what stays. I like writing everything out. That way I know for certain, because I know if I try to do it all in my head, I'm probably going to mess up somewhere. So the x minus 4 and the x minus 3 are going to cancel out on the top and the bottom. The x plus 4 and the x minus 3 are going to cancel out. And here the x plus 4 and the x minus 4 are going to cancel. So let's see what we're left with. We have a negative 3 times x plus 4, and then minus a 2 times x minus 4, and then that's equal to a 10 times x minus 3. And here we go. All this work that we've done is just to get the x's out of the denominator. Now we can actually go and solve this problem. Let's go ahead and distribute negative 3x minus 12 minus 2x plus 8. Notice I'm trying to be careful with the signs here. That's equal to 10x minus 30. So negative 3x and negative 2x is negative 5x. Negative 12 and 8 is negative 4. And that's equal to 10x minus 30. You'll notice this one actually doesn't simplify to a quadratic. So I actually don't need to do any factoring or zero product. I just need to solve for x. So I'll add the 5x over to get a 15x. I'll add the 30 over. Let's see. If I add the 30 over, 30 and negative 4 is 26. So x is equal to 26 over 15. And that's our answer. Now, of course, we should go back and check this. We should go ahead and plug this in for x. I do that on the answer key, and it turns out to work. It actually does work if you go and plug this one back in. So I won't show any of that work. You can see that on the answer key, but it's important to make sure you go back and plug that in. It's so important, in fact, that I forgot to do that during the video for this. So, Gene, good catch, by the way, on that. It turns out in the video, the last problem, the very last one I do, I forget to check the work, and it turns out that solution is extraneous. So my bad on that, but this one will definitely work. Let's go ahead now and let's try one of the word problems from the advanced section. This one was a little more complicated, so I'm back into section 7.7. I'm going to look at problem 1 from the advanced. The reason that this was a bit more complicated was because we have a different setup this time. So in this situation, we're filling a reservoir. So you can imagine kind of like a sink. We are filling up this little reservoir, ditch, or pool, or like pond, whatever. And we have a pipe that's pumping water into it. So here's the pipe. I know, great drawing. And water is coming out of the pipe, and it's filling the reservoir. Okay? But here's the problem. There's a drainage pipe in the reservoir. So a pipe can fill this reservoir in 16 hours. But there's also a drain. Think of this kind of like in a man-made pond or something that is to control the water quality or whatever. There is a drainage pipe put in as well that can drain this out, and it might take it to a septic tank, or it might drain it off somewhere else. And it can drain the entire filled pond in 24 hours. So one pipe can fill the pond in 16 hours, and if I open the drainage pipe, it can empty the whole reservoir in 24 hours. So how long would it take us to fill the reservoir if the pipe was left open? So now we have a bit trickier of a situation. This is one where I'm pumping water into the reservoir, but water is also leaving at the same time. So let's take a minute and let's think about the setup here. We have the rate of, I'll say the rate of the pipe that's pumping water in, and then I have the rate of the drainage, the rate of the drainage pipe. And together that should give me the total rate that it takes to fill the reservoir. Well, that's kind of a weird situation, right? Because the pipe filling the reservoir and the pipe draining the reservoir aren't working together. They're actually working opposite each other, right? One's filling it, one's pulling water away. So it's almost like we aren't really adding these together, because if I said the pipe can complete the job in 16 hours, so it can do one job for 16 hours, and the drainage can complete the one job in 24 hours. So hopefully this makes sense. The pipe can fill the reservoir in 16 hours. It can move all of that water in 16 hours. And the drainage can empty the reservoir in 24 hours. It can move all of that same water in 24 hours. That should give us how long it can complete the job. So I add these together, but that doesn't make sense. Instead of adding them together, subtract them. That should make more sense, because really that's what's going on. You're doing one thing's doing a task, and the other is weakening the task. It's lessening the rate of time, okay? So it actually should take us longer than 16 hours, right? If the pipe can normally fill the reservoir in 16 hours, but we're pulling water out at a certain rate, it should take us a bit longer. You might have noticed this sometimes. People sometimes when they were younger might have played at the sink where they would plug the sink with a stopper, and you'd try to fill the sink, but sometimes the stopper wouldn't always hold and it would drain just a little bit. So you got to put it on full blast to really fill the sink as much as you can. Maybe people did that. I did that when I was younger. So why? Because I was preparing for these types of problems, I'm sure. But this is the idea. You need to think that they're now not working together, but they're working directly opposite from each other, okay? So in this situation, let me clear some space here. Let me rewrite this. We have 1/16 minus 1/24 equals the 1 over x. So 1/16 minus 1/24, and I'm checking that on my calculator, I get 1/48 equals 1 over x. So basically x here is just 48. It would take us 48 hours to fill the entire reservoir. That's because not only are we pumping water in, but we're letting it escape as well. So this is the setup to this problem and what's going on here. We have the same thing going on in problem 2 from the advanced practice. In this problem, there's a hole at the bottom of a child's plastic swimming pool, okay? And it can drain the pool in 60 minutes. If the pool had no hole and we were filling it with water, it would only take about 40 minutes. So how long would it take the hose to fill with the hole in the bottom of the pool? One, you'd probably just want to go and get a new pool. But if we had a little swimming pool, I'm just going to make it a little rectangular thing, and we had a hose that we are pumping water into the pool for. So water's in the hose, comes out, and it fills the pool. But the problem is there's a little tiny hole at the bottom. So let's say that hole is right here. Now we have water escaping. Oops. We have water leaving the pool. So again, the hose and the hole in the pool are working opposite each other. Okay? One's trying to pump in water, one's trying to move water. So we know that the hose, it would take it about 60 minutes, about an hour to fill the whole pool. While the hole can drain the pool in 40 minutes. Basically, the hose can move all the water it needs into the pool in 60 minutes, and the hole can take all that water and pull it out in 40 minutes. Let's see here. So to move all of that water, to complete that one job of moving all that water, it takes the hose 60 minutes. And to move all of that water, to complete one job of that, it takes the whole 40 minutes to drain everything. Since they're working opposite each other, one's filling and one's draining, we have to subtract their rates, and that's going to equal the total rate and how long it takes us to actually get all that water together. So 1 over 60 minus 1 over 40, that should give me oops, wait a minute. I think I read the problem wrong. Oh, shoot. I read this problem wrong. It takes 40 minutes to fill and 60 minutes to drain. That should probably make more sense, right? The hole isn't that gigantic. So let me swap this around. It's negative 160 and positive 140. My bad on that. Sorry. So when I combine these together, I get 120. 1 and 120 equals 1 over x. So x is 120 minutes. So if it takes me 40 minutes to fill a pool and 60 minutes to drain it, here's my setup. Here's the negative 160 and the positive 140. It would take me pretty much 2 hours to fill the entire pool. Hopefully these problems are making sense to you. I'm not really seeing any comments in the live chat. If anyone has any questions, please let me know. Shoot me an email. But I think we're probably going to bring the stream to an end right now. I'll get this posted up right after we finish up here. And again, let me know if you have any questions. Shoot me any emails. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know if you have any questions or anything else you'd like me to go over. And otherwise, good luck with the homework. Keep me posted, and take care.